Alright, silly people, here's the situation. We're going to construct a couple more linear transformations, given descriptions of the transformations, and also do a couple of series of transformations and see what we get. Um, so if you watched my last video yesterday, you will have seen this diagram, right? This is representing a rotation of angle theta around the z-axis. So you're looking down the z-axis and you're rotating counterclockwise with angle theta. What if instead you wanted to look down the x-axis, so you're looking down the I hat vector, and do the same thing, rotate with angle theta? Well, then all you'd have to do is recognize that now you'd be looking down so that this is j hat, this is going to be j hat prime, this is k hat, and this is going to be k hat prime, right? And so all you need to do is pretty much use the same exact transformation equations. So the I hat prime is going to be equal to I hat, since that's what we're rotating around. J hat prime, oops, J hat prime will be, from the diagram, just cosine theta I hat, or that's actually cosine theta J hat plus sine theta k hat, and then k hat prime looks like minus sine theta j hat plus cosine theta k hat, right? Then we can quickly construct this rotation matrix then, just by going down the columns. So I hat prime is 1, 0, 0. J hat prime is 0 cosine theta sine theta. And then k hat prime was 0 minus sine theta cosine theta. So that's going to be t sub x for the future. If instead you wanted to look down the j hat unit vector and rotate with an angle theta counterclockwise around that, you would just have that this is now k hat, so this is k hat prime, and then this would be I hat, and this would be I hat prime. So writing down the transformations, now we have that I hat prime equals minus sine theta k hat plus cosine theta I hat. J hat prime is equal to j hat. K hat prime is equal to cosine theta uh, k hat plus sine theta I hat. So the new rotation matrix T sub y, just writing it down from the equations, cosine theta 0 minus sine theta for I hat prime, 0, 1, 0 for j hat prime, and sine theta 0 cosine theta for k hat prime. Okay. The next transformation that Griffiths wants us to look at is one where you just flip I hat with j hat. So you're saying I hat prime equals j hat. Have j hat prime become minus I hat, and you have k hat prime equals k hat. So this is just going to be a 90-degree rotation looking down the z-axis counterclockwise, right? That's what it represents. So the matrix for this, which Griffiths wants us to call S, is going to be 0, 1, 0, minus 1, 0, 0, 0, 0, 1. And then I'm assuming that this is a orthonormal matrix. I'm not going to prove it, but I'm going to say right now that the inverse of this is going to be equal to the transpose of it, which is going to be 0, minus 1, 0, 1, 0, 0, 0, 0, 1, which represents a 90-degree rotation clockwise with respect to the z-axis. So that's cool. So if that's how it is, then what is the quantity S T sub X times S inverse, uh, or in other words, T X S transpose. Um, so what's going to happen first is you take whatever basis you have, you look down the k hat direction, and you rotate 90 degrees clockwise. Then Tx happens, which we know is going to look down the I hat direction and rotate with some angle theta. And then you do S again. This time you rotate 90 degrees counterclockwise with respect to k hat. So it should just be equal to a rotation of said angle theta around the j hat unit vector. And we can test this. So we're going to line these matrices up. S was 0, 1, 0, minus 1, 0, 0, 0, 0, 1. Tx was 1, 0, 0, 0 cosine theta, sine theta, 0 minus sine theta, cosine theta. And then the transpose of S ended up being 0, minus 1, 0, 1, 0, 0, 0, 0, 1. So just doing the first or the last couple of matrices, multiplying those together, you get 1, 0, 0. So you have so you have 0 here, minus cosine theta here, minus sine theta here, 1, 0, 0, 0, minus sine theta, and cosine theta here. And then just multiplying those two matrices now, you get cosine theta, and then 0, and then minus sine theta, and then 0, 1, 0, sine theta, 0, cosine theta. And that is actually equal to ty, so that is what we expect. Then Griffiths asks, what if we do S T sub y S inverse? So you rotate 90 degrees clockwise with respect to the z-axis. Then you rotate around j hat with angle theta a little bit. And then you rotate 90 degrees counterclockwise around k hat direction. So it just looks like you're rotating around the x-axis with an angle minus theta is what it looks like. So just looking at that, we have 0, 1, 0, minus 1, 0, 0, 0, 0, 1 times, and then t sub x was, or t sub y was cosine theta, 0 minus sine theta, 0, 1, 0, sine theta, 0 cosine theta. And then S inverse was 0 minus 1, 0, 1, 0, 0, 0, 0, 1. So just doing the latter two of those matrices, multiplying those together, I'm getting 0, minus 1, 0, cosine theta, 0, minus sine theta, then sine theta, no, not sine theta there actually. Actually, yeah, sine theta there, 0 here, and then cosine theta here, right? And then doing those multiplied, looks like 1, and then 0 here, and then 0 here, and then 0 here, cosine theta here, and actually minus sine theta here, 0, sine theta, and then cosine theta. Okay, um, so we can make use of the fact that cosine is an even function, so this is actually equal to cosine minus theta. Sine is odd, so this is equal to sine minus theta, 0, and then again, sine is an odd function, and cosine is an even function. So yeah, this does look like t sub x rotating in the negative, the clockwise direction. All right.